In this video, I'm going to solve this second order homogeneous differential equation. This differential equation has a few characteristics. One is that the coefficients A, B, and C are constants, and the characteristic equation has complex roots. So given this, let's go ahead and try to solve this differential equation. We will make the assumption, the standard assumption, that y is equal to e to the power rt is our solution. That will give you y prime is equal to r times e to the power rt, and y double prime is going to be equal to r squared times e to the power rt. If I plug in these values into the equation, differential equation, we get the following. A r square plus b r plus c times e to the power rt is equal to 0. So the product of two factors or two numbers is 0. This one cannot be equal to 0 because it's an exponential function, and then in that case this must have to be equal to 0. So a r square plus b r plus c is equal to 0. Since the roots are complex, so that means characteristic equation for this quadratic function or quadratic equation is b squared minus 4ac, which must be less than 0. So we'll have two roots. Let's call them r1 and r2, okay? So r1 and r2. So r1 has the following feature. They are complex conjugates, so it's going to be r1 is equal to, let's call it lambda plus I mu, and R2 is going to be lambda minus I mu. So these are complex conjugates. So my solutions are going to be, so let's call it y1 or y1 of t is equal to e to the power lambda plus I mu times t, right? Because this is my r, this r, right? Then y2 is gonna be e to the power lambda minus I mu times t. Now I could simplify it slightly and then see what happens. So my y1 becomes, if I simplify it, is gonna be e to the power lambda t times e to the power I times mu t, okay? And my y2 is gonna be e to the power lambda t times e to the power negative I times mu t. So these are two solutions. Now we know that any linear combination of this y1 and y2 is also a solution to the differential equation, right? So my general solution in that case is going to be y of t is equal to c1 y1 plus c2 y2. Of course, so y1 is a function of t and y2 is a function of t. So let me just put a line down here. So now y1 and y2, their linear combination is going to be a solution. So let's go ahead and write it out exactly what we find. So y of t is going to be equal to e to the power c1 times e to the power lambda t times e to the power I mu t plus c2 times e to the power lambda t times e to the power negative I mu t. Now at this point we kind of want to look at this e to the power I mu t or e to the power negative I mu t. What does it mean? It's a complex number. We started off with a differential equation that has real constant coefficients, but we landed with complex numbers or imaginary numbers. Now, how do we go about doing this? Can we get real solutions? To do that, let me go ahead and do something on the side. Let me remind you of something that you have seen. Remember, e to the power x is equal to summation n is equal to 0 to infinity x to the power n over n factorial. Remember that rule, which if you write out, this is going to give you 1 plus x over 1 factorial plus x square over 2 factorial plus x cube over 3 factorial plus dot dot dot. Okay, using this formula or this power series expansion, you can substitute x by I mu theta, mu t, not mu theta. So if I replace x by I mu t, I'm gonna get a similar expression. And if you simplify it a little bit, okay, by taking into consideration, so let me just go ahead and write it a little bit. So e to the power I mu t is gonna be equal to just 1 plus I mu t over 1 factorial plus I square mu square t square over 2 factorial, and you can keep writing it out. So that will give you nothing but e to the power I mu t is equal to cosine mu t plus I sine mu t, okay? So that's what we are going to get. Now, similarly, e to the power negative I mu t is going to give you cosine mu t minus I sine mu t. Now you can go ahead and plug in these values into this equation. So that's going to give me y of t is equal to c1 e to the power lambda t times cosine mu t plus I sine mu t plus c2 times e to the power lambda t times cosine mu t plus it's going to be minus I sine mu t. And that's technically your solution. However, we kind of want a real solution, as I said. So what we could do a couple of things. C1 and C2 are arbitrary constants, right? You can make them whatever you want. Just look at these two expressions. You'll notice that if you plug in C1 is equal to 1/2 and C2 is equal to 1/2, then you're going to get, so let's say C1 is equal to C2 is equal to 1/2. If you do that, and then you're going to get a new solution. Let's call it U of t, okay? U of t is going to be nothing but e to the power lambda t times cosine of mu t. In a similar way, if I assume C1 is equal to C2 is equal to 1 over 2i, I'm going to get another function. Let's call it V of t. And V of t is going to be e to the power lambda t times sine of mu of t. Now, this U of t and V of t are actually solution to the original differential equation, which can be shown, by the way, by finding the Wronskian. This is a topic for another video, by the way. But just to give you an idea, so let's say, what is Wronskian? Wronskian is going to be, let's say U is one solution, so U of t, okay, and V is another solution, V of t, and find U of t, U prime of t, V prime of t, and take the determinant of it, okay? That's the Wronskian. Take the determinant. If the determinant is non-zero, then these two are independent solutions, okay? As you will see, if you do the calculation, the determinant or Wronskian is going to be non-zero. As a matter of fact, the determinant or the Wronskian is going to be this number. So W of U of t comma v of t is going to be equal to mu times e to the power lambda t. Actually, it's 2 lambda t. That's what it is going to be. And mu cannot be 0 because we are dealing with complex roots. Remember, our solution says the roots are lambda plus I mu and lambda minus I mu. If mu is 0, then we are dealing with real solutions, right? And then the complex case doesn't even arise. So mu cannot be 0. So that means if mu is not 0, this whole expression obviously is not 0. Okay? So that means that the Wronskian is non-zero. That means this equation, this solution and these solutions are linearly independent, meaning that these are solutions that you can use to find general solution. So finally, your solution, let's call it y of t. Again, how many y of t's we have had is equal to c1, some constant. This c1 may not be the same as this c1. So some constant times e to the power lambda t times cosine of mu of t plus c2 times e to the power lambda t times sine of mu of t. And that, by the way, should be your solution to this differential equation, which has complex roots. I hope that this discussion was helpful. Thank you very much.